should we start? Should have started before that, I guess. I think you've already.
Yeah, just started recording.
Okay, got it. So thank you, Don, for handing me the floor, I guess. And thank you, everyone, for attending. I wish I could give this presentation in Blacksburg, but due to some constraints, we could not do that. So let's get ahead. And as Don, I just want to add a few points about myself. So I'm a PhD candidate in the news lab under Dr. Walid Saad. I've been a PhD student direct PhD student ever since 2018, and I've started working on terahertz bands ever since then. So basically, by 2018, by then, there were no actual results on terahertz. It was really unheard of. And 6G was very nascent back then. I mean, now you kind of hear a lot about industry talking about 6G. You hear a lot of even academic papers that kind of address specific 6G requirements. But back then, we were really at the beginning, and we started to develop these fundamental analytical frameworks that would like prepare the floor and lay the analytical framework so that everyone has the way to start. So we kind of paved the road with these fundamental analyses in terahertz frequency bands. And we did not limit ourselves to physical layer analysis. It was basically on addressing wireless surfaces like VR and XR, basically extended reality. So that was our focus. Today, I'm going to cover some highlights on the role of the terahertz frequency band in 6G wireless networks. We call it a fellowship of communication and sensing, and you will understand really why as I go through my slides. But basically, this is really the key characteristic of terahertz, the joint communication and sensing property of it, which we have discovered over the course of my PhD research study. So let me get started with the talk. So in order for us to define 6G, I always find it fundamental to define what is not 6G. So what is not 6G? 6G is not only defined by an increased network capacity. So every single time, whenever we have a new network generation, usually it comes in every decade, people would think that, okay, 4G is just like an evolutionary version of 3G, where you would have a higher capacity and a higher data rate. But 6G is not that, and I'll clarify a little bit more about that. So if we look at the evolution of wireless generation, all the way from the beginning of traditional internet between 2G and 4G, basically back then we had that rate-centric evolution between these generations. And all we cared about was to go from a simple text message, right, to transmitting media, transmitting data. And here the sole reliance was on internet protocols. AI was unheard of back then. And then 5G came in and stepped in. And with 5G, we are no longer focused on the rate-centric evolution anymore, because 5G came in three big thrusts back then: IoT, MMTC, and eMBB. eMBB is still that evolution of 2G and 4G, but the Internet of Things was really the landmark of 5G communication networks. And here we became device-centric. We have reached to the point where everything has become interconnected. Our devices are all interconnected. You can have home automation, agriculture is interconnected. You wear a wearable now. You don't only have a mobile device, but a wearable. And here, given that the computing resources have started becoming much better, right? AI has started also its evolution hand in hand with the wireless generations. And in here, what happened basically is that AI was added as a layer on top of already established tasks like channel estimation, like internet protocols that we relied on in 2G and 4G. Now in 6G, it's a completely new story. Instead of just having things that are connected, we're basically interconnecting everything. We're really reaching a place where we have this new buzzword, the metaverse, right? Back then, when I was starting to work on XR and VR, we did not have the metaverse as a buzzword or as a keyword, but basically we were teleporting user to this virtual paradigm. And basically we need to have everything now interconnected. And we're really talking about an experience of the user. I'm not longer concerned about the quality of service, how much data rate I can get on my mobile device. What I really care about is my experience high, right? Am I satisfying a very high level of experience at every user, at the end user? And sometimes the end user can be a human being that is experiencing the metaverse or a particular service, and sometimes the user is trying to mimic a human being. Like, for example, any autonomous device that is trying to mimic the human intelligence of a user. And now, instead of just having AI as an added layer on task, we're reaching this overarching goal of AI native wireless networks, where AI is really fundamentally built in the infrastructure and the backbone of the wireless network, because we want to deliver this experience and because we want to deliver that different kind of breed of service rather than just a stream of bits that are delivering a particular data rate for just streaming a Netflix video. So exactly what I'm saying, the Internet of Everything is not just a scaled 5G, a scaled data rate from previous generations. And the key characteristic services would be XR services and holographic teleportation, which are sending us to this metaverse, I would say. Industry 4.0, and now we're reaching Industry 5.0 too, and digital twins, connected robotics and autonomous systems, and non-terrestrial networks. Now, in each of these services, the experience is different from one another, right? As I mentioned previously, that we are no longer only focused on equality of service. So the goal now is to get that frame of experience and try to be able to match it to the user. For instance, in XR, if I take that experience and try to translate it into a wireless metric or a wireless KPI, it's basically providing a high downlink reliability and a 5 senses synchronizations, because I want to have the Internet of Everything, and by the Internet of Everything, I mean the Internet of senses. So my senses need to be all interconnected. And I also, when I'm teleporting a user, right, I need to guide every communication link with tracking and sensing and situational awareness. So if I'm putting on a helmet and I need to move within a VR game or an XR game, the wireless base station and the network needs to be aware of micro-mobility and micro-orientation, that is the 6 degrees of freedom of me as well as of my surroundings, in order for it to provide me with that experience that I wanted. And in Industry 4.0 and digital twins, and again, we have now 5.0, digital twins are basically having a cyber twin and a physical twin. The cyber twin is allegedly in the metaverse, and the digital and the physical twin is basically that complex service, like an autonomous system or a complex manufacturing example that I want to teleport to the cyber world or to the metaverse. And what I can do there is either run experiments and try to see if I do this, then what happens, because I have now critical services that I don't want to perform decision-making in the physical world. I'd rather take that risk in the cyber world. And they can also be mimicking that physical complex system, right? So it can be two different goals. There are like simulation twins, and there are like mimicking twins or real-time twins. Of course, it always needs to be real time, but what I meant is just that it's mimicking it at every single point in time whenever the physical twin is evolving or changing. And here, for example, a key wireless metric is the synchronization of these millions of sensors of this physical twin with how it's connected in the metaverse or the cyber world and the cyber twin. And here, one key challenge of the wireless network is to predict these evolutionary dynamics and future states of these large-scale errors that need to be in sync between those two. And then we have connected robotics and autonomous systems. Here, the challenge would be to transmit real-time interactive 4D maps or even a higher dimension in optimal time-space boundaries. Of course, these connected robotics and autonomous systems, as I mentioned earlier, can exist in the digital twin paradigm. Again, it depends on the application. And here we have versatile control, localization, and communication requirements that have very tight requirements, and they need to be satisfied all together. And then non-terrestrial networks comes in to really merge the digital divide that we have and try to remove it, because today we have households that have very high connectivity and a very easy access to the internet. Meanwhile, we still have rural areas where the internet has not reached. So we need to have this service continuity on a global aspect. We need to have a continual coverage, and to reach that, we need to have a satellite that is interfering. And whenever we have those low Earth orbit satellites and these CubeSats, which are small, which are more energy efficient than other satellites, we can really get closer to the goal of deleting the boundaries between that digital divide that exists between whoever has internet access and whoever doesn't. And now I will highlight how these four key aspects, for these key use cases, can be key potential use cases in terahertz frequency band. And I'll also highlight why terahertz frequency bands are fundamental or characteristic of future 6G wireless networks. So if we look at this spectrum here, okay, we can see that at sub 6 gigahertz, we have your conventional vanilla services, the Internet of Things, your mobile devices, where your goal is to really execute or have a service that is just whatever we're accustomed when we say, I'm having access to the internet. And then when we go towards a higher frequency band, we can see that we have these high rate, high mobility services like connected robots, autonomous vehicles, like a platoon of autonomous vehicles, etc. And at the same time, you can see that there is another sensing dimension on top of the communication dimension that I can also serve those high rate, high mobility services. So millimeter wave bands can provide me with this rate that would be enough for those connected robotic autonomous services that that require a high rate but are also highly mobile. So they would require a potentially larger range than what terahertz can provide. At this stage as well, sensing provided by millimeter wave can be provided via the radar sensing that would provide me with object detection within a range that I would want. Then we go to XR, digital twins, the metaverse, and here these are very high rates. So the rate that is needed is higher because I am really transmitting an XR content that requires data rates that are much higher that millimeter wave cannot fulfill even with massive MIMO. We can see in here that at the same time, the terahertz frequency band can provide me with a highly accurate or a high resolution sensing, meaning that I'm really providing the user with the micro mobility and micro orientation tracking and sensing input, as well as that high rate. So it's a win-win situation. And this is why we really named and coined this talk as a fellowship of communication and sensing. So recently we've published a paper in IEEE Communication Surveys and Tutorials where we have identified 7 defining and unique features of terahertz frequency bands, which are the quasi-opticality of the band, meaning that it's just at the boundary between radio and optical frequency bands. We've found terahertz tailored wireless architectures that are key for terahertz, that are different than what we've seen so far. The synergy with lower frequency band, joint sensing and communications, physical layer procedures, spectrum access techniques, and real-time network optimization. We've also highlighted 4 candidate potential use cases, which are XR, holographic teleportation, digital twins in Industry 4.0, connected robotics and autonomous systems, and non-terrestrial networks. And today I'll be highlighting, as I've already highlighted the use cases, I'll be highlighting those 7 defining features and how they can help us take terahertz from just on pen and paper and actually deploy it in future 6G networks. So one might ask me, like, the terahertz frequency band has existed for ages. If it's so powerful, if it's so good, right? Why haven't we deployed it before, Christina? And here I would say that we've always had difficulty, not only at the wireless level, we had a difficulty at device level, at the transceiver level, because previously we had what is so-called the terahertz gap, and actually the terahertz frequency band is the last frequency band that was discovered across the frequency spectrum. And because of that, we had a problem of where if I want to take a semiconductor device and I want to produce a terahertz frequency band, I cannot do that because the transistors and other quantum devices will have an electron transport problem, which is limited at 300 gigahertz. And actually, as you'll see in my talk, that is why anything that is after 275 gigahertz or 300 gigahertz is called real terahertz, and anything between 100 and 275 is called sub-terahertz, because it really doesn't have a molecular absorption effect that you will see as I discuss. And also, the transceivers are easier to manufacture at the sub-terahertz band compared to the terahertz band. And then I might say, okay, this is quasi-optical, forget about the semiconductor device. Let me get an optical device and let me try to produce terahertz with it. But again, here I will also have another challenge where the wavelength of those photonic devices can only be extended to a certain range, and I'm limited by 30 terahertz. So if I come from optical land, I cannot manufacture a transceiver that would help me produce terahertz waves. And if I come from the radio land, I cannot also produce that transceiver that delivers that terahertz band that is able to serve my wireless network. So how can I mitigate this now? So one key aspect that I haven't mentioned in the slide here is that let me just operate at the sub-terahertz band using optical or semiconductor. The second thing is that there are now new innovations that are occurring on the device level, where plasmonic devices and graphene-based designs that are a merged version of what is mentioned in semiconductor and optical that are gradually overcoming the challenges that I have just mentioned. And another reason why terahertz was not deployed in previous wireless generations is because we haven't needed those high rates that we wanted now. So whenever all you care about is just listening to music or streaming a video service, I don't care about the extremely high, gigantic data rates. All I care about is a mediocre enough data rate that can serve my application, because terahertz comes with a lot of challenges when it comes to the deployment, as you will see next. So let us refresh our mind a little bit on electromagnetics and how the wave would change when I go from microwave all the way to terahertz. So you can see that in microwave, and again, this would be like 120 degrees because you were taking like a particular sector of the cell, I am aware, but this is just for illustrative purposes. So a microwave is omnidirectional. As we go towards millimeter wave and terahertz, I'm becoming more and more directional. And you can see that in terahertz, the line of sight link has a different color than the non-line of sight link. This is because the gap in power between line of sight and non-line of sight has become higher. So I have higher path and reflection losses. Now I have a line of sight dominance in terahertz. It's all in or nothing. And my range is substantially limited compared to microwave, because in microwave, even if your base station is outside, even if you have walls, you don't care. And I have now something beneficial, which is a smaller antenna footprint. So the antenna is smaller, given that the frequency is inversely proportional to the wavelength. So I can manufacture an antenna that is physically small, but electrically not. So basically, this enables me to leverage the concept of massive MIMO more. And we can see that when this electromagnetic wave changes, the challenges that we face in wireless network as engineers to deploy these bands change too. And so the way we need to think in order to deploy those bands and eventually orchestrate resources needs to also change. So at lower frequency bands, it has always been a chase behind bandwidth. A chase behind allocating the resources in a way to improve the data rate because I don't have enough spectrum. And how can I increase the link capacity, right? Now at terahertz band, I have a very high data rate. I have that capacity that I have been always dreaming of, but I don't have everything else, basically. I don't have a robust network anymore. Of course, the network and the channel has always been uncertain, but now given that my link has become very susceptible, I am even more vulnerable to any changes in the network. My coherence time becomes smaller. And so now the goal, instead of chasing the bandwidth and chasing a higher link capacity, is to really rethink, okay, how can I redesign the architecture in a way to improve my coverage and suit those, directional links that I have now? And how do I leverage that sensing property of terahertz that is there and not lose it? So of course, that doesn't come only with nightmares, the line of sight link, even though it's challenging, it comes with some benefits. One benefit would be that you have an effective interference mitigation scheme because I'm very narrow. So the line of sight link would only come to me and not to my other neighbors, right? And this is really giving me that the allure of sensing and localization and tracking and the capability of having a data that is providing me information about the micromobility and the micro-orientation of a user. But the cons are I'm easily disrupted by blockage, so I can even block myself. There's even self-blockage. So if I'm wearing a helmet in XR, if I am in a position that is in a like a unfortunate angle to the base station, I would be blocking myself. I think we do that in life too, not only in wireless networks. But yes, so blockage becomes an issue. And the problem is it's not only static blockages that are easily deterministic, any other person can block you from your serving base station. So almost everyone becomes the enemy, right, towards your link. And the problem is that human behaviors are highly uncertain. We really cannot, the way you move in your bedroom, the way you walk in your house when you're trying to grab a bite from the fridge is very different than the way you run and jog and move in an office. So the dynamic blockages really depend on human behavior. And if I wanna optimize my beams in a way to suit that human behavior so that nobody in the room blocks me, it is really challenging and it depends on the type of surrounding environment. Next, molecular absorption effect. Basically, the molecular absorption effect is a phenomenon that results from the difference in energy between the higher and lower energy states. So this is common to all electromagnetic waves, not only for terahertz. The only difference is that at terahertz, it has a highly pronounced effect, and this is why we start talking about it. And as I've mentioned previously, the molecular absorption effect has an okay effect up until 275 gigahertz. As I go from 275 and up, I start having problems. So you can see in here that I'm okay, and then boom, the absorption lines start to appear, and I need to be very careful into how I operate. The other problem is that these windows in here, right, are not they are not static or deterministic. They change with the way the oxygen and water vapor in air change. So we need to be very careful. So, and this is another reason why terahertz communications is more suited to indoor areas rather than outdoor areas. So basically, one of the first 7 defining features is quasi-opticality. And this is where the molecular absorption effect becomes a double-edged sword in here. because this enables us to improve significantly terahertz sensing capability. And what I discuss in this slide is really beyond wireless networks. I would say it's really on the environmental sensing level, where this can be used in environmental sensors, where you would really try to analyze gas compositions, detect substances that are not detectable by optical or visible light communications, and analyze water dynamics. I just wanted to add this slide as well, that terahertz frequency band not only can be used for wireless network for 6G, but can be also used for sensors and analyzing gaseous compositions in environmental sensors. Now, how is that quasi-opticality beneficial to us when it comes to 6G, right? So the terahertz bandwidth allows us to have that high resolution environmental sensing, and that is a byproduct of a high bandwidth, because the Kramer-Rao lower bound of sensing is correlated and proportional to the bandwidth. So the higher my bandwidth, the higher the resolution that I can achieve. And now when I have a larger array or a RIS, like a reconfigurable intelligent surface, I can improve not only the resolution, but also the precision and the specificity of sensing. So terahertz can enable me to say that Christina is moving 1 centimeter to the left, 1 centimeter to the right, and in degrees. What the RIS enables me to do, or the large antenna arrays allows me to do, is to basically say that I don't want to characterize Christina within one point in the 3D domain. I want to characterize it via multiple. That are enabling us.
Hi, so Christina, we can't hear you anymore.
I think you lost me.
Yeah, we did.
Okay, let me reshare my screen. Also, one more, can you see my screen now?
Yeah, I can see your screen.
And when I move, because it's telling me your screen is paused. Oh. Hold on. Can you see now quasi-opticality and stuff?
Yeah, I can see it. Okay. Thank you.
And one more thing, that this figure is not from our experiments. It's an experiment that has been done in Dr. Hornet's lab, but we have put it here for exposition benefits, but we haven't cited it in the presentation, given that this is being recorded, just FYI.
What school is that?
It's Dr. Hornet in Northeastern lab. So they have had like a hierarchical bandwidth modulation scheme where they try to measure those windows. So I just wanted to put this figure in here to explain to you where the absorption lines appear and why anything that is below 275 gigahertz is beneficial.
Okay, thank you.
Sure. So let me continue. So I think we've reached here, and we said that the quasi-opticality beyond environmental sensors is beneficial in terms of situational awareness, because it's providing us with this these active base stations that are allowing us to have instantaneous location and orientation information at the centimeter level in 3D space. So now my base stations are aware. The key is to take that data, and if we have a good AI system, is to predict stuff about the environment next. So this new breed of data can be used for beam management, mobility management, and blockage avoidance. Of course, I can use this breed of data on the fly on a computational setting, but I would be benefiting more about in in this data if I deploy those AI schemes that would allow me to take that data as input data and predict stuff. So not only use it for computational purposes, but also use it to predict. Now, one question would be how to strategically deploy terahertz networks. And the second key characteristic that we have, or the second unique defining feature that we have identified about terahertz is the unique architectures. So one might ask that, is ultramassive MIMO enough? What happens when the cells are smaller and smaller? So if you imagine with me, as the antenna's footprint becomes smaller, right? My range is also becoming smaller. My range when it comes to base station to UE, the cell size is becoming smaller. Now, every single time I'm at the edge of the cell, I'm at really the worst case scenario. And anytime I'm at the center of the edge, I'm at the best case scenario. So now we have a scenario where the best case and the worst case scenarios are very far from each other in terms of performance, but very close to each other when it comes to distance. So if we deploy ultramassive MIMO on a cellular level, the pros are that I have that pencil beam forming in an achievable and scalable way. And we have those multiplexing benefits as well between multiple data streams. But the problem is that ultramassive MIMO, the real benefits of it were really reaped at the lower frequency band that assumed a Rayleigh fading channel, because that would say that I have channel hardening and I have those favorable propagation settings that would allow me to predict stuff. And here I don't have them because the terahertz channel is not Rayleigh and it's highly, it's really directional, right? So I only have a line of sight and maybe 1 week non-line of sight if I'm lucky. So one must think about like, what are the ways that I can minimize that effect of big difference between best case and worst case scenario. So here we would say that let me maybe remove those cell boundaries, and that way I'm no longer hurdled by the effect of a cell boundary and cell edge. And here I'm using that baseline operation scheme of massive MIMO, but instead all I care about is the local CSI at each base station in contrast to the global CSI. And of course, as we go towards terahertz frequency bands, acquiring the CSI becomes much more difficult because the channel is low rank and highly sparse. So, high rank and low. Yeah. So, and then the problem is that with these is that as we have the cell-free massive MIMO, how do I make it scalable? I always have to have these base stations connected to a particular core, and then I go into another problem where again I need to gather multiple CSIs now. So even though this allows me to mitigate handover failures and intermittent links at the cell edge, I'm still not at the point where you can be scalable, highly scalable. So we are always falling into the problem of either scalability at one end where I'm at cell-free massive MIMO, or I'm at the edge where I'm at the cell edge or at the center of the cell, and I have this big difference. So my service keeps on being intermittent, and I don't have that continuous link that I would want, which is highly reliable. So cooperative RISs are another key component of future architectures that would enable me to have a successful terahertz deployment. The reason why is because, as I've mentioned previously, in terahertz frequency bands, the chase is no longer behind the bandwidth. The chase is now behind intelligence and behind customizing the channel in a way to make my line of sight links more robust and to guarantee them all the time. What RISs provide in here is that they can allow me to customize the wireless propagation environment in a way to guarantee that line of sight link that I wanted. Now, why cooperative RISs? Because users are highly mobile, of course, right? And now I want to increase the level of control that I have in order for me to orchestrate the resources that I want to provide to the base stations and the network. And I want to really get to a point where asymptotically, I'm mimicking the behavior of a multipath propagation environment. Why? Because now we have multiple virtual line of sights provided from that RIS. And we have the actual line of sight links that are provided from the base stations and large antenna arrays, of course, if the RISs are passive. And even if they're active, I have now multiple links, right? And whenever that happens, I can improve the spatial multiplexing capabilities. So if we go back to ultramassive MIMO, now we're really mimicking whatever Rayleigh channel that we had. We don't have the line of sight dominant channel that we previously had. And now I can benefit from the favorable propagation characteristics of ultramassive MIMO and have a more robust link. So it's a win-win situation again. Now, on the electromagnetic wave level, one might think also that there are many other benefits to RISs. So, excuse me. So with terahertz bands, we can really coin the term holographic RISs. And when we say holographic, is that asymptotically, we are reaching the point where we have the continuous spatial aperture, meaning that the antenna arrays now can be very close to each other. And in fact, when you reach terahertz and real terahertz, that is beyond 300 gigahertz, you are no longer limited by a spacing of lambda over 2 between the two antenna, the sub-arrays. You can go a little bit lower that bound. And that enables us to reach that asymptotic continuous aperture and achieve higher spatial resolution and enable the transmission and detection of EM waves by leveraging that spatial frequency components. So this really enables us to go one step further in sensing because we're really capable of assessing signal processing capabilities that we wouldn't be able to assess before if we only have a non-continuous aperture array. And I'll go one step further and talk about near field RISs at terahertz, where again, with this dense architecture, and given that we're operating at a short communication range, we might fall into the scenario where we're satisfying the co-phase condition and we're operating in near field in contrast to far field. And that would mean that now we can benefit from the curvature of the wavefront to reduce synchronization and reduce a lot of other resources in the network. Because again, if we go back to sensing, now we can perform particular signal processing on the wave where I'm not seeing the wave in its linear behavior, but in its wave where like the curvature behavior. And now I can get the phase of arrival, which opens the doors for new sensing capability. So we can get more for less data, right? We're getting more information for the same amount of electromagnetic waves that we are getting into the RIS. Another thing that I always like to remind people when we talk about 6G and future wireless networks is that when we go to new generations, we can no longer think about one frequency band that is major and is the only frequency band that would satisfy all services. Because we've reached to a point where now we have services that are mature enough and that have enough rate that is being satisfied, but a new breed of services keeps on emerging, right? And with those new breed of services emerging, now I need to match a new frequency band to that new breed of service. As I showed previously, we have that high spectrum. For example, high rate, high mobile services would benefit from the millimeter wave. The lower mobility ones, but extremely high rate needing services would benefit from the terahertz frequency band. And vanilla services would benefit from the sub 6 gigahertz and below. And basically, this is why whenever we talk about terahertz frequency bands, we always need to talk about this synergy with lower frequency bands. This not only allows us to fulfill multiple use cases and diversified requirements, but this also allows us to reach the goal of a universal coverage and deliver a more scalable network solution. Because with terahertz alone, with its limited range, despite RISs and despite the architectures that I have explained previously, we cannot really achieve that universal coverage that we want. So this is why this integration is necessary. So at the beginning, it can be done by information showers that are overlaid on top of the existing network that we have, right? So I have a high band network, 5G high band millimeter wave. Now I add to this network multiple base stations that are serving as information showers. And these are deployed, for example, to serve particular use cases that would benefit from this rate. So for instance, if we have this autonomous vehicle setting in here, whenever that autonomous vehicle passes by that information shower, it can offload a lot of data, acquire new information, and then carry on with its connectivity to other millimeter wave base stations. Not only we're reaching that universal coverage, but we're improving the continuity, the reliability, the range, and sensing mechanisms. Because as you've mentioned previously, sensing doesn't come in a single flavor. It comes in multiple flavors. And for instance, when it comes to services like XR, what I care about is high resolution sensing, micromobility, micro-orientation. But terahertz does not allow me to detect an object that is 40 kilometers away from me or 10 kilometers, not even 1 kilometer away from me. And here, new frequency bands or like the older frequency bands need to interfere and merge themselves with terahertz or have this synergy in order for us to deliver that 6G solution to the user at the end. And now we have those new network slices. So if you remember in 5G, you always have that triangle, which is eMBB, ultra reliable, low latency, and URLLC. But in 6G, we have now probably 6 network slices. And these 6 network slices cannot be delivered if we don't have an integration between multiple frequency bands. However, that with more complexity comes more challenges always, right? So we now have to have new hybridization techniques that would allow us to join those multiple frequency bands together to maintain the load balance that we have and to orchestrate the resources in a seamless way. Joint sensing in communication systems is one unique and defining features of terahertz frequency bands, and I think it's one of the most important ones, and it's also a pillar of 6G wireless networks, not only with terahertz, but with multiple frequency bands. So one might ask me, why now? Why not before? Why didn't we have radio nodes before that could do joint sensing in communication? The answer is twofold. The first reason why is because sub-6 gigahertz was omnidirectional. So I could not really localize, track, and detect with a high accuracy where the user is located. Also, the wireless services themselves did not have that sensing input needed as a part of its functionality. So all we cared about was communication, right? All you cared about is like streaming a particular video. You did not care where that person is located. But as we move towards the Internet of Everything and services that are more complex, we really need that new form of sensing input. So for example, an autonomous vehicle can never operate if it doesn't have good sensing facilities. Otherwise, all the cars would hit each other on the highway. This comes not only with opportunities and advantages at the functionality level, but it also comes with opportunities and advantages to the network and core perspective. So first, we can use every sensing, we can use every communication challenge as a sensing opportunity. So if I have a blockage, I would say, let me use that same signal to characterize the blockage that I have, and then from that point, learn it on. And actually, this is a framework that we have proposed. We were the first to propose a joint sensing and communication framework at the terahertz band, which I will cover in the next slide in more detail. But basically, every communication challenge is a sensing opportunity, and the other way around too. Every sensing challenge is also a communication opportunity. And now again, this sensing information is a new breed of data. Now I have continuous information about how my environment is changing. So a mobile device is basically a new eye that is providing me information to the base station about what's going on around me. It's a little bit scary when it comes to security constraints, I guess. That also needs to be scrutinized. And we are efficient in terms of spectrum because now I can allegedly use the same waveform, spectrum and hardware for both sensing and communication purposes. And it's cost efficient, of course. But of course, the challenges in deploying joint sensing and communication is that what is the optimal waveform from a signal processing perspective that would allow me to reap benefits in terms of communication and sensing performance? And what are the ways to have these two different functionalities exist? So we recently published a conference paper in ICC, which was taking place in Seoul in South Korea in May, on joint sensing and communication to achieve that situational awareness in wireless terahertz systems. And in here, we really took an example, an XR application. This can be extended to more applications as well. But XR is really important in here because in XR, as part of the functionality of the service itself, we need the 6 degrees of freedom of the user in a real-time setting, or at least near real-time, or best effort, I would say, with whatever terahertz can provide us. And then we also want to sense what's happening in the environment. So what we do in here, we take that uplink signal. So now here we have an RIS that is acting as a base station. So we really learned the lessons we gained from the 7 defining features paper. So we really are leveraging joint sensing and communication. We are deploying an architecture that has RISs in order to benefit from the virtual line of sight, to benefit from the small antenna footprint, etc. And here we're taking the uplink signal and we're using that uplink signal, basically the same waveform, spectrum, and hardware for both sensing and communication purposes. And again, the model here is that every RIS is basically acting as a terahertz operated base station. That's why I said it's active. It also has an MEC server for the XR content, because the XR content not only has very tight communication constraints on the wireless network itself, but it also has computing constraints because the XR content is huge. And basically that is why it needs terahertz to begin with. And here the RIS service has an array of sub-array structure. So the methodology that we use is basically to take the signal, okay, and collect multiple signal realizations from the wireless environments. That is, we record multiple snapshots from the uplink and use those measurements both over line of sight and non-line of sight. I will not go into the details of the methodology, but basically what's happening is that in line of sight conditions, we're gathering the situational awareness in terms of tracking. So we're really collecting the 6 degrees of freedom of the user in near real time, because we have a computational layer that needs to occur. So we cannot really be at 0 end-to-end latency. And in the case of line of sight, which is often forgotten at terahertz, it's forgotten because the gap between line of sight and non-line of sight is large. So if we do want to use non-line of sight for communication purposes, it provides us with a very low data rate. Then it really defeats the purpose of communication. But for sensing, all I care about is to do signal processing on the received signal, right? And now I can use that signal to gather situational awareness about that terrain or environment. And now, instead of discarding that link, we're really using it to assess the situation of blockages in a room and use that to be better when it comes to communication. So if we look at the simulation results in here, we can see that as we increase the bandwidth, the granularity of our visualization becomes substantially better. Meanwhile, as the bandwidth is smaller, of course, the granularity is not that high. But this is good news because it's a win-win situation. So as we're increasing the bandwidth, the data rate is increasing, the resolution is increasing. This might be a challenge if we're in a setting where even the spectrum, terahertz spectrum is crowded, but I guess this is a postponed headache for now. So this visualization is really calculated on the go, and it's averaged at every point in time whenever a new link is like resulted, whether it's like line of sight or non-line of sight. Now we really take that breed of data and we assess the reliability and the total spectral efficiency of my system. And we really want to see how well do we do, right? So we can see that our highest gains are achieved in a low mobility setup. That is a 10% improvement compared to, and the 19% improvement for 20 users. But the idea is that it's really good in low mobility because we have the computational burden of the tensor decomposition method that we have. So if the users are too fast, I cannot change my beams too quickly in a way to match their speed. But if they are in a low mobility setting, my computational burden is not that high. I don't have to lag with the users. Now, when it comes to spectral efficiency, we're really doing quite well compared to perfect CSI if you look at the figure, because basically it's a byproduct of the framework that we propose, which uses the same waveform, hardware, and spectrum. And again, this is the first work that kind of adopts this framework. Now I jump back to the 7 defining features. I just wanted to give a highlight on how joint sensing and communication can see surface in sub-terahertz and terahertz frequency bands. And this is a work that is going to be extended into a journal where we really take that breed of data and try to predict, right? So again, how you take the data, what you do with it is really kind of gives you more leverage in order to make a piece of art when it comes to the results. So when it comes to physical layer procedures, right, the channel at terahertz, excuse me, becomes more difficult to predict or even calculate because it's highly dimensional and often very sparse as a byproduct of the line of sight link, highly dimensional because we have a large number of antennas there. So this leads to a significant overhead. And at the same time, the channel is highly varying because we have a very small coherence time as a byproduct of the frequency of operation. So here we really, again, AI is the answer where we really need to use partial CSI instead of like full CSI to predict accurately the instantaneous CSI of the network, because partial CSI is not enough to fulfill the needs of services like XR. And here we need to, for example, exploit the concept of multi-agent generative ML, where the way we can find the channel matrix is not via classical schemes, but via generative schemes. Initial access when it comes to physical layer is a problem. We have what is so-called the deafness problem in terahertz. So because the links are very narrow, prior to any communication, right, we have a deafness problem because the links are too narrow, they're doing this, they're sweeping, and they could not meet each other. So we have like a deafness problem. It's as if I'm speaking in one frequency band, the other guy is speaking in another frequency band, and we cannot hear each other. But this is not really a frequency problem, it's really a spatial problem. Here comes the role of lower frequency bands, as I've discussed previously, is that they come to serve new services that require different functionalities and different flavors of rates, but they also come to help terahertz do better. So if I use the half omnidirectional initial access schemes that are operated at millimeter wave or sub 6 gigahertz, I can then locate the UE and the base station, and then I can move forward. Or I can rely on sweeping sensing beams in here, but that would be more time consuming. So it depends on the architecture and the use case of case. Spectrum access techniques is another unique defining feature of terahertz, and it's basically needed to change at terahertz because OFDM cannot really work well at terahertz. So the reason why OFDM does not work well is as we go towards higher frequency bands, and particularly at the uplink, we have the peak average to power ratio becomes really pronounced. That problem becomes pronounced, so we need to improve the system capacity. So if we want to improve the system capacity, have multiplexing and multiple access, we need new techniques. One key technique that comes from the optical domain rather than from the radio domain is OAM. So OAM has been used for optical links, and because terahertz is renowned to have that quasi-opticality we talked about, we can use OAM as a new dimension for multiple access without exhausting any time or frequency resources. The other good news about OAM is that it can be generated using meta surfaces. So if you really want to know what OAM is, if you remember from our physics classes in high school, the EM wave has a helical beam and it has a spin, which has plus and minus modes, which can only be multiplexed in 2 dimensions. And then you have the helical momentum or the orbital angular momentum, which can be used with almost infinite, or at least claimed infinite OAM modes, where you can multiplex your information on multiple helical beams. But again, this is a nascent research area that still needs a lot of research for maturity. So I advise people to work on this because this can help us achieve multiple access and multiplexing for future frequency bands. Now, one question that I don't have the answer for, but it's really an open problem, is how can we multiplex sensing and communication functionalities using OAM, since it's a multiplexing avenue? Another spectrum access technique that is more vanilla, I would say, is NOMA. And NOMA really becomes good for terahertz frequency bands because, as I've mentioned previously, when we have a smaller cell, the gap between best case and worst case becomes big. And NOMA is known for its capability in shrinking the gap between best case scenario and worst case scenario. So now the cell edge and the center of the cell are closer to each other, both on a physical and performance level. Another reason why NOMA is good is because terahertz is gonna take place and see light with the large antenna arrays and RISs. And it has been shown that NOMA can improve the service of the users with RISs even better, and it can improve the system whenever the SINR is high. So with terahertz, given that we're benefiting from high bandwidths and we can really benefit from a higher SINR as well. Real-time network optimization is the last key defining feature of terahertz wireless systems. The reason why real-time is because the use cases have become complex. You cannot be non-real-time in the metaverse. You cannot be non-real-time in XR or in digital twins, right? So that's the wireless requirement that I need to fulfill. Now, can terahertz do that? Can terahertz provide that real-time network optimization? There are many challenges affecting terahertz robustness, The first one would be that the channel is even more stochastic than ever. We're susceptible to extreme events. By extreme events, we mean the fades, interference, blockage, self-dynamic and static blockage. Now I'm no longer deploying terahertz on its own. We have multiple frequency bands, so we have heterogeneous frequency bands, and the complexity of the network is growing. We also no longer care about communications only. So we're migrating towards this concept of versatile wireless systems where we need to have a joint resolution rate and even control optimization. And on top of all of that, we have compound channels as a byproduct of RIS enhanced networks and the architectures that we need to use to deploy terahertz efficiently. So how can we minimize all of these headaches, given that I don't have an equation that would solve all of those challenges? One can tell me, let the data explain how I can be optimizing the network in real time, right? Give me the data, since everything is uncertain, and since our knowledge about the channel and the network is minimal. The problem with that is it's not also easy, because the data at terahertz is non-stationary, and the centralized machine learning scheme would fail to comply with the low latency requirements. And we have a scarcity of the data because the data is, again, non-stationary, isn't changing as a result of the small coherence time. And on top of that, I want real time. How can I do that? Of course, new out-of-the-box ML frameworks are needed, and they need to be explored for solving those aforementioned challenges and for solving the issue of scarcity in data and non-stationary data. So here we give a simple key example where we really showcase what is really happening in the wireless network. And we're really saying here in that we really need a distributed multi-agent network optimization where the learning agents of our network, them being a base station or an RIS, an active RIS that is, it needs to have generalizable techniques and as well as specialized techniques. So because not all terahertz cells operate in the same fashion as a result of the dynamics of people, the environment itself, indoor or outdoor, etc., that agent operating in that particular environment needs to be specialized with particular mobility pattern and a beamforming angle. But it also needs to help via the core or the edge, its other base stations or access points that have a common denominator with it. For instance, maybe they all share the same molecular absorption level when they're all indoor with the same humidity level. They all share maybe the same coherence time. So it's important to leverage data in a way to help us and be our friend, not our enemy. Again, new challenges arise in here when it comes to the seamless cooperation between multiple agents, data sets, and the intra-cluster variations due to time varying data, meaning that even if I'm specialized within my network, let's say, or within my cell, new unseen instances might appear due to the fact that terahertz is highly susceptible to network or channel conditions like blockages, or a new breed of blockages comes in. What do I do then? And how can I be more robust and learn how to learn? So we really need a new breed of generalizable data. We're saying meta learning in here, but we really mean more than that. We really want to learn how to learn. And to do that, we need to go beyond learning a simple data set. We want to map the heterogeneity of the network to multiple tasks and reach that overarching goal of a high generalizability, meaning my base station, which is acting as a learning agent, can generalize to new unseen instances, and these new unseen instances are out of my domain or out of the distribution that I've been seeing. Now, on pen and paper, achieving that generalizability might be possible, but the question is, can we do it in real time? Can we infer in real time and achieve the high rate, reliable, low latency characteristics of VR or XR services? That's the question that needs to be answered properly. So I've previously exposed the key use cases that are going to be key for 6G. And here I'm answering how terahertz would be able to enable these 6G use cases. So for XR and holographic teleportation, where when in indoor, the molecular absorption level as a byproduct of the different humidity level at indoor areas would be controllable. So we can have better ranges. And the range in an indoor setting is also smaller. So terahertz here allegedly can potentially reach the high rates that I would want, as well as the high resolution sensing that is needed by XR and holography. With Industry 4.0 or 5.0 and digital twins, if the setting is controlled and not subject to high mobility, meaning we won't fall into the beam disalignment and blockage problems, we can really sense environmental changes in the physical and the cyber domain with risky outcomes, and we can have that tight synchronization into play. When it comes to more outdoor and highly mobile use cases like connected robotics and autonomous systems, if these services would require 4D maps and high resolution maps that would require rates that are higher than millimeter wave, terahertz can be deployed and can be used to also sense micromobility and the micro orientation to provide this fine-grained autonomous driving, for instance. But of course, it needs to be done hand in hand with lower frequency bands in order to sense further targets. And finally, with non-terrestrial networks, the molecular absorption loss at lower heights than 16 kilometers becomes minimal, right? And now terahertz becomes an avenue that is no longer disrupted by molecular absorption. And now we are more robust than optical links, yet we still have a high bandwidth. So that is why terahertz is a candidate for non-terrestrial networks. To conclude, terahertz is not here to come and replace all frequency bands. It's going to have a slow start in future 6G generations. So it can start as a overlaid information shower on existing high band millimeter wave networks or existing 5G networks. The goal is to migrate from pure communication radio nodes that do only communication, and we're really going towards this versatile wireless network and wireless systems where we have a joint sensing and communication function, which expands itself to multiple other functionalities like control and localization. We're going towards holographic surfaces that are characterized with the small antenna footprint, as well as a continuous aperture to reap the curvature of a wavefront and reap more sensing benefits in terms of signal processing. And again, 6G and future generations must be characterized with an integrated frequency band scheme. We can no longer operate with one famous frequency band because our services are diversified and their requirements are even more diversified. And finally, the role of ML and AI becomes more pronounced because we are no longer chasing bandwidth, we're chasing everything else, and we need that human-like intelligence ingrained in the network. So in order for us to deploy terahertz frequency bands in future 6G generations, we really need an AI native wireless network to do it properly. That is all from my end. If anyone has a question, I'll be glad to address it. And I don't want to keep you late on a Friday afternoon.
Okay. Thank you, Christina. Thank you for your presentation. So I do have one question.
Go ahead.
What's the most important use case for 6G, for terahertz?
What's the most important use case for terahertz? So I would say anything that is high rate needy is, of course, key use case for terahertz. Like, as I've mentioned before, most of the performance analyses and the optimizations that I have conducted are for VR and XR, because those devices would require, in order to satisfy a particular quality of physical experience, a higher rate that cannot be fulfilled with millimeter wave. And when we talk about XR, we're not really talking about the early generations of VR or XR. We're talking about ultimate XR or higher levels that would require that high rate. And at the same time, here terahertz is not used for communication only, it's used for sensing and communication, because terahertz is really characterized with beautiful sensing properties that are not existent in previous frequency bands.
Okay, thank you. So you talked about using terahertz for sensing and communication. But what's the trade-off? Like, so you can talk about the advantages, but what's the trade-off? What are you trading up when you're using for sensing?
So
what's the trade-off?
In the framework we provided, actually, if you look at this figure in here, of course, so two things. Now there is a research that is going on into, like, let us find the waveform that is optimal to do both sensing and communication, because with communication, you're really, you have a usually different waveform than sensing, right? But in here, because we used a tensor decomposition method, we were able to use the communication waveform itself. Now, we were limited a little bit by computing, and this is why you can see that our reliability is still not perfect, right? Compared to perfect CSI. We're still behind perfect CSI as the mobility grows. But that is as a result of the computing delay that is there. Now, probably that would be the trade-off. But even with beam tracking, you have a delay. In any setting, you have a delay. The reason why we don't really have a trade-off is that the high bandwidth has a twofold benefit. A data rate improved and a resolution improved. I would say one parameter that we can tune is the waveform. So can we come up with a waveform that can improve sensing and communication? And then we would use that same waveform, and that would enable us to use easier signal processing techniques, or maybe an easier setting, which would allow us to match or be closer to perfect CSI. But there is no fundamental trade-off in the proposed framework in here. It's a really win-win situation.
Okay, thank you.
Sure.
Does anyone have any questions for Christina?
There's something in the chat.
Okay, well, yeah, go ahead.
What makes terahertz more robust than optical? No problem. Yeah, so first, hi, Will, I hope you're doing well. In regards to terahertz being more robust to optical, is that if we go to, let me go to this figure. Okay, so from an electromagnetic perspective, physics tells us that as we go from visible light towards radio, we're more robust. And that is why we've used radio so far in life. We haven't used visible light communication, because first, the range achieved is larger. So the range that terahertz can achieve is larger than the one that can be achieved with optical, number one. Number two, terahertz are less, like the beam of terahertz is larger than the beam of light. The beam of light is infinitely small, right? So it's even more susceptible to blockage, to the network itself. Like, just like I can really block the light with like a paper or any opaque surface, that makes it very difficult to do anything in life. So the range is larger with terahertz, and I'm less directional than optical. So these are the two key features why terahertz is better than optical. Does that answer your question? Okay, awesome. Thanks, Will. Anything else?
Thank you, Christina. Thanks for your presentation. I enjoyed it.
Sure.
Thanks to everyone for attending.
Thank you. Thank you, everyone, and have a great Friday afternoon.
Yeah, have a good Friday.